Hello, everybody. This is Jeff Martin. I'll be your host for today for the Propeller Assembly Language webinar. I wanted to start out by saying I'm really excited to have everybody here. This webinar actually generated a lot more excitement than I think any of us actually expected. We've got quite a few people. There's still some people joining us, and we have over 150 people that are registered for it. And I wanted to thank you in advance for all the great questions you've had when you registered on the registration page, because they helped me figure out how to structure this course based on your needs. Unfortunately, I'm not going to be able to get to every question during the webinar, but I will follow up with you on all those questions via email or phone, however you want to communicate. So it's the top of the hour, so I'm going to go ahead and get started. First, I'll show you what we're going to do, what the format of this presentation is. We have an hour and a half of time scheduled. We're going to probably be doing I'll be talking a lot during the first 45 minutes to an hour, presenting a number of topics, and then the last part of the webinar will be basically an open Q&A session where anybody can either type their questions in or ask questions verbally, and I'll try to address those. For this webinar, all your microphones are muted so that we have a good, clean audio source. And you may ask questions via the questions window. It should look like this that you see on your screen down here. Those, I think that I don't recall. There's some kind of a setting that appears at the bottom after the first question that you enter that I believe indicates who you should send the question to. If it gives you a choice, I believe it's like send it to organizers or to staff is the one that you want to choose, unless there's a particular person that responded to you already. And just so you know, two of our education staff, Andy and Stephanie, are my assistants today. They'll be monitoring your questions that you entered in the questions window and answering those or fielding those to me as needed. Also, during the talk, you may raise your hand if you have an immediate question. This is really good if you want to voice your question over your mic or phone connection, and especially if it's something that has to do immediately with something I'm discussing at the moment or just finished discussing. Otherwise, feel free to enter your questions in the questions window, and we'll try to get to them whenever we can. Just to start out, I wanted to show you our group's experience. If you remember when you registered, there was a question on there about what your level of experience is with the Propeller chip, and this is the breakdown of it. And you can see that about 2/3 of us are in the beginner or haven't used the Propeller chip category. So there'll be quite a bit of the webinar today that will be addressing the needs of those of us. And then there's about 1/3 of us are intermediates as well that probably have some really good, probably advanced questions actually. All right, so what I'm going to do is begin with a little illustration of how the Propeller works. This is to get everybody on the same page, especially those of us who have never used the Propeller and perhaps haven't seen any literature on it. The Propeller is a multi-core device. It has 8 cogs that are exactly alike, and except for 2 things. Each one has a unique ID, which is 0 through 7, and the first cog has a unique duty on Propeller startup. Cog 0 is the only processor that starts up when the Propeller is powered up or reset. All the others remain asleep. And because of this, the Propeller application that you download when you're developing, is always started in cog0. After that, it's up in the air. It's up to you, the developer, to decide whether the application runs solely in cog0 or whether it launches other cogs to run different parts of the application. So just wanted everybody to know how it's very flexible that way. The number of active cogs can change at any time too, dynamically as required for speed and power conservation purposes, or to perform any combination of independent or cooperative functions. Let's take a look at Propeller memory. In the Propeller, there is a couple of blocks of shared memory, RAM and ROM, 32 kbytes of each. And this is shared amongst all the cogs. Every cog has access to it, but they have mutually exclusive access to it. They take a round-robin approach to actually reading and writing. Basically, they get a little window of opportunity to do a read and write. That way they can't clobber each other's write to a single atomic entity. In addition to this, inside each cog is 512K longs of space, or 2 kbytes of RAM. And this is really important because without this, the Propeller would not be as fast as it is, because every cog would be sharing main RAM all the time. And this is a point of confusion for quite a few people. They think that because cogs share main RAM, that the whole thing runs kind of slow. But actually, most of the time, cogs do all their processing inside their own cog RAM, and very little time accessing the shared RAM. And sometimes they'll access shared RAM in bursts. So overall, the effect is quite minimal, and you get a very fast system where every cog that's running can perform simultaneous functions. And then here's another point of confusion that I'd like to clear up for everybody before we move further. Propeller applications. When you take an application and compile it in the Propeller tool, it gets converted into a binary image, and that image gets downloaded to the Propeller's RAM. It can also optionally be stored in the Propeller's external EEPROM for use upon the next startup. But either right after download or right after startup, the Propeller application, both spin and assembly code, live in the main RAM. So it's important to keep that in mind, that the application doesn't live in any of the cogs at the moment, just in the main RAM. Also, it's important to note that every cog can only run assembly code, or code written in assembly. They can't actually run spin code directly. And so what actually happens here when the Propeller starts up, cog0 starts up, loads the application from external EEPROM or downloads it from the host, and then it loads up a spin interpreter from ROM, and that interpreter, that's an assembly-based program, that's what actually runs in the cog, or any cog that's running spin code. As that interpreter runs, it fetches little bits of spin tokens from the main RAM and optionally writes data back. Actually, quite often it writes data back because all the variable storage for the application exists in the main RAM rather than inside of the cog. Okay, so, and then if the spin application decides to launch another cog, and perhaps a cog to run some assembly code, this is where things get a little bit different. The Propeller starts up another cog and loads up the actual assembly code direct from the application from the main RAM into the cog that was started. From that point on, we have 2 or more cogs running, and things continue as normal, where in this case cog0 is interpreting spin code, and cog1 is running assembly and possibly reading and writing from the main RAM, but not necessarily accessing the main RAM ever. It's up to how the application's written. So, and then you've heard me mention it already. There's two built-in languages in the Propeller, Spin and Assembly. Spin is many of you actually have used Spin, which is a good thing. So you know a lot of this. It's high-level, object-based, pretty easy to understand. It is interpreted, but it's still pretty fast. It's on the order of tens of thousands of instructions per second. And not a lot of people think about this fact, but it actually generates high-density code. I'll explain what that means in a moment. Propeller assembly, on the other hand, is a low-level language. It's compiled or actually assembled. And it is super fast, like 20 million instructions per second if you're running at 80 megahertz clock speed. And that's just in a single cog. With all the cogs running, that's 160 MIPS in a 3.3 volt 9 by 9 millimeter package, which is pretty incredible. It is also lower density code, and you might recall I said lower density code. The Spin code is high density, or higher density, really. And what we mean by this is because in assembly, every instruction that I'll show you over here, like this move instruction, it takes one long of space. In Spin, every instruction gets compiled into tokens, and the tokens aren't necessarily a long in size. They might be a little bit more, or they might be a lot less. So what ends up happening is, because it's not compiled, it's tokenized, and it's interpreted at runtime, the Spin code to achieve the same function in assembly code actually requires just a little bit less space, and in some cases a lot less space. So that's just something to keep in mind when you're thinking about which language to use for a specific task. So why would you want to use assembly? Well, one reason is speed, and the second is speed, and the third is, of course, speed. It's really fast. There really isn't very many other compelling reasons to use Propeller assembly over Spin that outweigh the major gain in execution speed. In fact, nearly all the features of Propeller assembly are also built into Spin. So if you don't need a special feature of assembly or the speed, then feel free to use Spin. There's no reason not to. And something to keep in mind is that there is a trade-off regarding development time and runtime. In Spin, just like many other high-level languages, the development time is relatively fast. The runtime is slow. That's relative, of course. And in assembly, the development time is typically pretty slow. The runtime is very fast. As you program more in assembly, you'll get faster at programming. It's unfortunate that it takes so long for most of us. Don't feel bad if you feel like you're crawling through it when you're writing a program in assembly, because the rest of us are like that too, and there's lots of little enhancements and optimizations that you can do that might take a couple of days to figure out. That's pretty typical of an assembly language programmer. So let's take a look at a space and speed example. What I'm going to do here is open up a little program that I wrote called Speed Test. This is a combination Spin and assembly program. Let me expand this here. Okay. Now, don't worry if you don't understand everything that's on here yet. We'll go through things a little bit later. But what I wanted to show you is that I have, this is my, the routine that will be running most often in this code in Spin. And all it's doing is setting an I/O pin to an output and toggling that pin as fast as it can. Also, down here is a piece of assembly code. It also happens to be 3 lines. And it's doing the same thing, but on a different pin. So both Spin and assembly here are going to try to toggle a pin as fast as they can, and we're going to take a look at it on the scope to see what happens. So I'm going to go ahead and download this and see if I can take a snapshot for you. Okay, so Here's a snapshot of the image. The trace on the top is the spin code, and the trace on the bottom is the assembly code. And you see I'm at 4 microseconds scale here. So the spin code is taking about, what is that? That's about 11 microseconds, it looks like, to toggle in between each toggle. So that little routine right here, the repeat and the out A loop, takes about 11 microseconds in this case to execute. Meanwhile, down below, it looks like a bunch of, well, just a bunch of garbage. That's the assembly cog that's actually running at the same time, toggling the pin very fast. And I'm going to show you a sample here from, let's zoom into that. Okay, here we go. Sorry about this. Never mind the little capacitive and inductive phenomena here. Something's wrong with my scope or my setup. The propeller is actually generating a nice, clean square wave, but I couldn't get that looking clean before the webinar. Anyway, so now we're here. The spin code is still running, and it's generating quite a long pulse here that's off the screen. And we see that the assembly code is toggling once every 100 nanoseconds, which is exactly what I would expect it to be. It's quite a bit faster, so it's like hundreds of times faster. Okay, so that gives you an idea of the difference. Let's go ahead and start talking about some coding here. Since most of you are familiar with, Jeff Ledger says, that's not a prop scope that I used. No, it isn't. It's my Tektronix scope. The object structure for the propeller. Every object that you write is separated into different parts of code using these block designators. Many of you are familiar with those, like con, var, obj, pub, pry. Those are for your spin constants, global variables, sub-object declarations, public and private spin methods. And then at the bottom is dat, which is for data, and it's also for propeller assembly code. That's where your assembly code actually goes. Let's see if I have an example here. Well, yeah, this is the example. Con, pub, pry, and dat. Typically, code is written this way too, in this order, but it doesn't really matter. You can flip these all upside down so that the cons are at the bottom. It'll still compile the same way. Okay, and then for those of you that aren't familiar with assembly, I'm going to give you a little bit of insight into the nature of it. For one thing, it's all about math. I mean, ultimately, every computer is just manipulating numbers all the time. Different combinations of instructions that do that end up making really nice things happen that are very user-friendly. But it's all math. It's just manipulating data, moving data around, adding, subtracting, and applying logical operators and whatnot. So keep that in mind when you're thinking about assembly instructions, because that's all they're doing. And they're also very atomic, very small. They work in very small, simple steps. For example, add 2 numbers together or subtract 2 numbers, move a number from one place or another. If you wanted to do something like add 2 numbers, subtract another, and multiply the result by something else, you can do that in spin on one line of code, but in assembly you need multiple instructions. Let's see, 3 instructions in that case. So everything happens in very simple, small steps. And in propeller assembly, there's a common syntax where you have an instruction followed by operands. And usually the instruction has 2 operands, so it looks somewhat like this. So instruction followed by a destination operand and a source operand. And the names are very important there. The destination is what it sounds like. It's usually the destination of the result of the instruction. The source is some source value that it's using for the instruction. Now they all behave a little bit differently, and you can find out in the propeller manual exactly how they treat these two operands. But for the most part, if there's two operands involved, the destination's on the left, the source is on the right, and it performs an operation and stores the result back in the destination register. An example of this would be, say, the add instruction. This is an actual assembly instruction, add x comma y. In this case, it's adding like this. It takes the value that's in the y register, adds it to the value that's in the x register, and stores the result back in the x register. And a similar thing happens with the subtraction command. It takes the value from the y register, subtracts it from the value in the x register, and stores it back in the x register. Very simple, not a whole lot of complexity to that. Many instructions operate like that. There's something else to say about the common syntax here. There's also some optional parameters. You see, I told you about instruction and operands, but there's also an optional label, condition, and effects fields that are included in every assembly instruction. This doesn't include assembly directives like org, let's say. Only the instructions that actually run at runtime. Let's see some examples of this. Of course, the first example that I gave you fits within this. We're not using any optional fields for this add instruction. And here's another one that uses a few of the optional fields. We've got, this is a shift right command. It's going to shift the value in x by right by 1 bit. And it also has an optional label out here. That's just a symbol that we created on the fly, a unique symbol. And it could be used for a couple of purposes. One is to kind of give the line a name so that the code becomes more readable, but more importantly, it becomes a place that you can target and call back to or jump back to. The final field you see out here is an effects field, and we'll get into more of that a little bit later about how that works. A third example here with a subtraction command is with a conditional field. This actually causes the subtraction instruction to execute or not execute depending on the value of the C flag. And this is a very powerful feature of Propeller assembly that is unlike most other assemblies I've seen. In fact, I haven't seen any that do stuff this way. And I'll explain why that's important later. Okay, so organization. Assembly and data can be intermixed. As I said, they exist in the data section of the objects. And that's important because a lot of times assembly routines need some kind of initialized data ahead of time. So let's take a quick look at something here. I will look at, I'll just pick an object here. Okay, so here's an object, the quadrature encoder object. And you see I have a lot of assembly code in here. And if you look at the bottom, near the bottom, where the assembly code ends, there's a number of things defined. In fact, I have some comments here explaining it. These three items here are essentially what I'm treating as, to the application, they're just data. They exist in the application memory as the values that I specified, and they've been given a symbolic name. When you actually load assembly into another cog, depending on where these things sit, they might get pulled into the cog, and that's important because you can use that as some defined variables that you use within your assembly code. And that's what's happening here. This A mask, B mask, and MSB, these three longs, I want those values pulled into the cog for use by the assembly code and possibly modified by the assembly routine itself. And the assembly routine refers to them by name, A mask, B mask, and MSB in this case. Okay. One thing to point out is to aid in proper loading and execution, it's recommended that your features of your assembly and data be arranged like this. First, your assembly code, all the instructions that run at runtime, followed by any initialized symbolic data like the A mass, B mass that I just showed, and then followed by any reserved symbolic memory. That's memory that's not initialized but is pointed to by a symbol that your assembly routine can use. If you have those in a different order, it typically causes lots of problems unless you really know what you're doing. In particular because every cog starts executing the assembly code from address 0. It gets loaded into address 0 of the cog's register space. So if you have data up there, you're going to be trying to execute data, and of course many of us know that that's going to cause lots of strange problems. So here's an example of how this gets loaded up. And I have an example little assembly source program on the left side. I'm not showing the spin code that's required to launch it. We'll get into that in a moment. But I just wanted to show you that when the spin application requests that another cog startup with this assembly code, say starting at the power of 2 label, this is what happens. Over here we've got cog RAM on the right side. The data gets loaded up starting from power 2 all the way through 495 longs of data. So whatever happens to be after this assembly routine and after the declared variables I've defined and the reserve space, that gets loaded up too. Most of the time it doesn't matter because you don't care what's there. You're not using that space. So on the right side now we have kind of an image of the cog map. It doesn't cog RAM, excuse me. It doesn't look exactly like this. It's assembled into machine code, but I'm showing it here symbolically for you. But I did change some things. If you notice that this move answer comma par command has now become move 5 comma 496. The 5 and 496 aren't numbers that it's operating on. It's actually the address, the register address that the move command will use. If you notice that the 5 here in the move command points down to the answer register, which is the 6th one down at index 5. That's where the answer label was calculated to be when the assembly code was compiled. And the 496 happens to be the location of the par register, which is a predefined register. The same thing goes for all the other instructions. That really what happens is an address gets stored of any symbolic registers that you've specified. That gets stored in the opcode that gets launched into the cog RAM. And the really important thing here is that these numbers have to be accurate in order for the code to run properly. And the way they get calculated is really based on this org statement that you see on the top left of the code. When you start an assembly language program, you should always have an org statement. It could be just the word org, or it could be org 0. It could also be some other value, but typically it's 0, and that's because the assembler will use that value, 0, as the base point to calculate all the symbolic references for. So, in other words, when it gets down to this move instruction, it internally thinks of that as being located at address 0 within CogRAM. This is all, again, during the compilation process. So it uses this to figure out what the actual offset's going to be for, say, the answer symbol or the value symbol. And if you had org missing or you set it to some other value, those symbolic addresses would be calculated differently, and your code would not run properly unless it was loaded at some kind of offset where everything lined up again. So case in point, just make sure you put an org statement at the top of your code. Okay, I am going to start switching over to doing a little bit more Propeller, excuse me, some looking at some code here. let me explain how this works. I'm going to pretty much ignore most of the spin code because I'm assuming that that most or all of you are familiar with spin, and just focus on the assembly code because that's what we're here for. The only thing in spin code that's important here is the cog_new instruction. This is the instruction that actually launches another cog, launches assembly into another cog. Cog_new just says, grab the next available cog, start it up, and start loading up my assembly code or whatever happens to be there starting at this address as in toggle pin. If you look down near the bottom, that symbol appears here, and it's on the first line of my assembly code. So that's my pointer to my assembly routine. And the second parameter there is what gets stored in the par register inside the cog. We'll get into what's important about that in a bit. For now, I'm just setting it to 0. So what happens at startup time, or excuse me, at the moment that the cog_new instruction is executed, is another cog starts up. It's commanded to start loading data from this point, this as in toggle pin line, and it continues reading for 495 longs, loads that all up into its cog RAM, clears the last 16 registers, which are 496 through 511. Those are the special purpose registers. And then it starts executing the code from address 0, which is where this move dir A line appeared. And this instruction is it's really a copy. It's kind of a long time sort of a legacy naming convention that was used. And what it's doing here is it's taking a number, this binary value 10, and moving it or copying it into the dir A register, which we're familiar with. That's the direction register for I/O pins. And you'll notice here that there is a pound sign in front of it. This is really, really important, and it's very easy to forget it. It's one of the most common mistakes made in programming in lots of different assemblies, not let alone propeller assembly. What that means is I'm giving a literal value, essentially, a number that I want you to use. If I left this pound sign off, then it would still compile, and what this means is go to the register pointed to by this value, grab the value that's in that register, and use that to copy into dir A. That's a powerful feature, too. A lot of times it's not what's intended, when you have small numbers out here. So one trick that I use to remember this is whenever I just think whenever I'm typing a number in here that's a number that I want to use, I'm thinking number. I need to put a pound sign there, a number symbol in front of it. But believe me, you'll make this mistake many, many times, leaving this out, and it'll cause strange behavior in your code. So somebody says, is it a hash symbol and not a pound sign? Yeah, I think different regions of the world call it different things. I call it a pound sign. It's also a hash symbol. Somebody asked, how long does it take to start a cog? Is it the same for assembly and spin? That's a good question. To start a cog, well, it takes just as long as it takes to read that memory. One thing I'm unclear about is whether, I believe that the hardware actually does load up 512 longs of memory from RAM. And then the last 16 longs it clears to 0, which is where the special purpose registers exist in the cog RAM map. So it takes as long as it does to do that, and that depends on what the clock speed of the whole system is. So also one thing to mention here, in case you didn't know, every cog gets a window of opportunity to access the RAM, the main RAM, once every 16 clock cycles. So let's see, if we're running at 80 megahertz, times 16, that's how long it'll take to get one access, 512 longs plus a little bit of overhead. Looks like it's about a little over 100 microseconds to answer that question. So every time you go to launch a cog for assembly, it'll be 100 microseconds. The same thing happens for spin code. It launches the assembly the spin interpreter in that amount of time, but there is extra overhead involved in running the spin interpreter, so it will be a little bit longer to actually launch another spin program. The assembly programs will launch a little bit quicker. Here's another question. Could this assembly program have been executed by itself without starting another cog? Yes. Yes, it could have. I could have, in fact, I'll show you this here. I could have changed this cog new to a cog init command, and if I knew what my cog ID was, I could have put that value here. I believe that this is the right syntax. The ID first, followed by the pointer and the last value. So this would actually cause my currently running cog to get overwritten with this assembly cog. And yes, that works. If you try to do the same thing with spin, that will also work. You can relaunch yourself with spin code, but it's a little bit trickier because there's stack space involved. So what you really want to do is provide new stack space for that new piece of spin code that you're launching into the same cog. Otherwise, there's a collision that occurs that the currently running cog starts modifying the stack space while it's also setting up the same stack space for a new piece of spin code, and things often get clobbered and then it doesn't run properly. But with assembly, it's a kind of a no-brainer. It just works. Thanks for that question. Here's another good question regarding org. When would you ever use something other than org 0? Honestly, I have never used anything than org 0. I've never had a reason to do so. However, I think that the reason for doing so would be if you're creating code that you want to be maybe dynamically loaded into a different section of an existing cog. For example, perhaps you're writing a large memory model assembler runtime that has a little bit of assembly in it and a space for loading additional assembly on the fly dynamically, because perhaps you can't fit an entire, maybe you have the need for a really large assembly program and it won't fit inside the cog RAM all at once. So what you could do is you could use the org command to specify the location where you intend to launch that little snippet of code into, and that way all the addresses will be relative to that offset. I don't know if there's any other good reason to use org for anything else other than 0, honestly. Somebody asked, what's the best way to test in ASM for a flag that's being set in spin? Okay, well, let's move on to another example code that we could kind of use to answer that question. Let's see if I can remember where I stored this. Okay, I'll explain this code a little more detail later, but what I wanted to show you is what I have here is up at the top of the spin code, I have a defined variable called count that's of size long. And then in my cog new, remember that 0 that I put as the second parameter? This time I'm actually passing the address of count by using the @ sign in front of it. So what that's going to do is basically send when the new cog is launched that's running this ASM code that I pointed to here, the par register is going to contain this address of count. And that's a way for the assembly code to actually receive a pointer to some piece of memory that the spin code which started it wants it to know about. So if you take a look, remember this is going to launch this assembly code, this ASM code right here. The very first instruction that I have here is a move address comma par. Again, what this does is it takes whatever is in the par register, that stands for parameter, by the way, the parameter register, and copies it into this address register, which I've defined down at the bottom as an initialized value that's equal to 0. Then from there, I can actually take that address and read or write main RAM using the read byte, read word, read long, or write byte, write word, or write long instructions. And in this case, I'm doing a write long. So what you would do to answer your question is you would pass a parameter in the cog new or via some other method to the cog that's getting launched. That parameter should be the address of some memory location that maybe contains the flags that you're interested in. And the assembly code can simply do a read long to get the value out of main RAM and check the flag and do whatever it needs to do. Okay, so, good question. As count changes in the spin code, is the change reflected in the ASM? It would be if it read it again. Remember that what's happening here is the assembly code's being run in its own memory space inside of the cog RAM. The spin variables are always out in main RAM. So when they get changed by spin, any assembly code that's using those values doesn't see the change unless it rereads the value. So you actually have to do another read long, read byte, read word, whatever it takes to get that. Conversely, if similarly, I guess, if the assembly code is actually modifying values, and that's what I'm doing here in this example, I'm actually just constant in a little tight loop where I'm incrementing a value by 1, and then I'm writing it out to the address that was passed to me when the cog was started. That's actually writing back to the memory that's holding the value of the count variable. And so the spin code can just keep referencing the count variable, and it will keep updating because the other cog, the assembly cog, is actually updating it. But again, that variable exists in main RAM, not inside of any cog. So once the cog reads it, it's free to change whatever value it read, and that won't affect the main RAM until it goes to write it back. Let's see. I'm going to go ahead and, here's another good question. Does write long behave just like other instructions like write long dest comma source, or is it an exception? That's a very good question. I remember when Chip and I were designing this, that this came up that we actually had it flipped around the other way because it kind of logically made sense that the destination is the address that you're writing to. Unfortunately, the architecture that would cause some extra hardware to have to be built in the cog just to behave that way, and because all the other instructions are destination on the left. And so what we decided to do is the destination always refers to a register within the cog. So in this case, the term destination doesn't make sense. It's the destination address that we're reading a value out of in order to write to the main RAM address pointed to by the source field. So we still call it destination and source, although it's kind of hard to think about it that way in the case of write long. Read long makes a lot more sense because you're kind of reading from write and writing into the value that's on the left. So it is, I suppose you can think of it as an exception, although in the terms of, or by nature of how we define the hardware, it's not really an exception when it comes down to it. Okay, I'm going to go ahead and, I know there's other questions coming in, but I'm going to try to get through some more material here, and then we'll open it up for more questions at the end. All right, so getting back to this speed test here, you saw what the signal looked like. This assembly code is toggling a pin as fast as it can, and it does this again. I didn't get quite all the way, but this move command moves the value binary 2, actually, or binary 10, which is decimal 2, into the direction register. That turns on the bit that controls I/O pin P1. So that sets it to an output. P1 is set to an output. The XOR command simply applies an exclusive OR logic operator to the value that's currently in out A. So in this case, the destination gets read. The source gets read, which happens to be the same value as was used above, decimal 2 or binary 10. And then that gets exclusive OR together and written back to out A. So as you know, an exclusive OR flips bits back and forth every time something is exclusive ORed with 1. So the effect of this is that we're writing either 10 or 00 to the out A register, which is toggling P1. And then the jump command simply jumps back to the loop, which is this XOR instruction. One thing you might want to pay careful attention to is that I use the pound sign or the hash symbol in front of the loop label here. This is very important because if I left this off, what it would do is it would go to the register that's pointed to by loop, grab whatever value is in that register, and use that as the destination to jump to. This is also a place where I, for one, have made a mistake many times leaving that pound sign off. Most of the time you want the pound sign or the hash in front of the destination that you're jumping to. But what if we didn't want this thing to run as fast as it could? What if we wanted to delay it by some amount of time? I've got some code here that does this, not that one. Let's see, wait count. By the way, I'll send the source code out to everybody via email that we use in this session. The wait count command is what we're going to focus on here. What I did here is I added 3 lines of code and some values, initialized values at the end. So at the bottom, I defined a time symbol that initially set to 0, and a delay symbol, which is 80 million divided by 1,000. That's because this is the delay, the amount of delay that I want to add in this pulse, or in this little loop. 80 million divided by 1,000. I did 80 million because I know I'm running at 80 megahertz. So what I'm going to effectively achieve is, by this, is a number that's equal to the number of clock cycles that are in 1 millisecond of time. This top line of code is exactly the same as it was in the previous example. I've added this line of code where I'm taking the value of count and moving it to my symbol time. Count is a special purpose register, the system, that points to the system clock, which is a value that just increments, starts up at some random value when you power up the chip, and increments one unit every clock cycle. So you can think of it as the current time. I move that into my time variable. Then I add to that time variable the value that's in my delay register, which is this calculation that I did at the bottom. So I'm going to add the number of clock cycles that I know occur in 1 millisecond. Then here's the key point. There's this special command called wait count. What this does is it basically puts the cog to sleep, all except for a little tiny piece of hardware that sits there and compares the value of the system counter to the value of the time variable that I've given it here. And if it's not equal, it just keeps the cog asleep. If it does equal, it wakes up the cog and it immediately executes the next instruction. So this is a way for you to delay and to also consume less power while doing it. So you're not sitting there waiting on a loop. You're actually kind of asleep. It works really well. And it has a bonus feature in it that you give it the next delay that you want to wait for, and it automatically adds that into the time variable. So once I set up my delay up here at the top, if I give it this wait count time delay, it's going to make me wait for 1 millisecond in this case, and automatically add 1 millisecond worth of clock ticks to the time variable. So the next time I come around, I'm going to wait for that time. Then I do the same thing here. The last two lines are exactly the same as it was before. And when we run this, we get a different signal that looks like this. And you can see my time resolution here is 1 millisecond. And this is right on the money. It's exactly, I mean, it never wavers. It toggles every millisecond on the dot. This is a really powerful feature, and one thing that's not so obvious about it is that it doesn't matter how many instructions you have in the loop here, so long as those instructions don't take more than the amount of time that you've set up for your time window. So I could continue to add instructions here before or after this XOR command, and my pin would still toggle once every millisecond, which is a great feature, and it's really super deterministic, absolutely necessary for writing little drivers and things in assembly. Okay. Again, if you have any questions about this, I'll try to address those here in the next few minutes. All right. Getting back to the effects field, this was an optional field that's at the end of every instruction, potentially. This is one of the unique features of the Propeller assembly. There are 4 effects that you can put there. It's the letters WC, WZ, WR, or NR, and that stands for write the C flag, write the Z flag, write the result, or no result. In other words, don't write the result. Now, in most processors, they have a set of flags. Remember how I said everything is all about math inside of processors. Every operation thus has potentially some mathematical states that might be of interest, like the C flag, which is the carry flag. So if you did a mathematical operation that overflowed your register space, the C flag would get set. In other words, you've calculated a number that's bigger than what you can store in memory. And so it's important to know if the C flag was set. And the Z flag is for 0. If the result of the last operation was 0, the Z flag is set. Most processors have these and possibly other flags, and they get affected every operation that you do. Conversely, in the Propeller, almost no instructions affect the flags unless you tell it to. And this is really important. Most of the time you don't care what the flags are. But there are other times where it's absolutely important to know what the state of the flags were after the operation. So instead, just remember that no flags get affected by default unless you have this write C or write Z out here. So if we see an example, we take my add instruction, add Y to X. I've put a WC effect out there. That means write the carry bit after the operation. So if the effect of adding Y to X caused the value, the result to be greater than what I can specify in a long, which is 4 billion something, the carry flag would be set. And that might be important later, and I'll show you how that gets used. So just keep in mind that that flag is set, and we can utilize it at some point in time. And that we can utilize that with conditions, which is the last optional field that you can actually include just before the instruction. These are just some of the possible conditions here. If E, which is if equal, if A, if the value was above, that's if you're doing a comparison. If C was set, or combinations like if C or Z, if the C flag was set or Z was set. There's many other examples and or conditions that you can use. Let me see if I can bring up an example here. By the way, this that you're going to see on the screen here is the Propeller quick reference. It comes with the Propeller tool. Don't know if a lot of people know about it, but in the Propeller tool, under the Help menu, you can select this quick reference PDF to choose that. Also, the Propeller manual is right there too, and the data sheet and some other things, some other resources. So again, if we go back to that quick reference, this is basically a summary of all the instructions, spin language and assembly language both. Near the bottom is a list of all the assembly conditions that I was talking about. Remember I said that I only showed 4 on the screen. There's all of these, what is this, like 32 or something. So there's all these possible conditions that you can use to trap certain states and perform code or make code behave differently based on it. So if we go back to our slide here, let's go. If we had that add x comma y and we write the C flag, later on we can put this if C in front of the jump, maybe a jump command. So let's say that in our case, if the C flag was set, it's some kind of an error. So logically, if C was set, I want to jump to some error routine. If C was not set when it actually reached this instruction, it does not execute this instruction. In effect, the instruction becomes a no operation. It does still take the same amount of time as executing. It takes 4 cycles all the time, which is what most instructions in the Propeller take. And that's important because a lot of times when you're writing assembly routines, you have multiple decisions that you need to make based on conditions that are, both a mixture of internal and external conditions. You have these different decision paths through the code. Each of those paths in typical assembly programs on other processors takes a different amount of time because there's different instructions involved. That's really detrimental, and we realized that, and Chip came up with this great idea to not write the flag states every time, only when we specify, so that you can save them till some point in time when you want to act upon them. So I could have any number of instructions in between this add and this jump command that don't write the C flag, and it will stay set to whatever it was when this add instruction was finished. And then later on I can execute an instruction based on it. And if that instruction doesn't, if I know that conditional execution isn't going to take a different amount of time, then even though I have logically different execution paths through my routine, I know that that path from the top of any particular point to the bottom of another point is always going to take the same amount of time, because it's essentially always going to be executing every instruction. It just might not do anything with the ones that were conditionally excluded during that iteration of the loop. So writing sensor readers and maybe drivers of some kind, signal generators, if you have different conditions, different decision paths through your assembly code, it's a lot easier to write code that is not going to cause any weird glitches in your signal. You're always going to have this rock solid signal being generated. Okay, so I hope that was understandable. Let's see, I know we're kind of approaching the top of the hour already. There is so much to be said about Propeller assembly that it is really hard to squeeze into a time like this. And I've really come to understand that as I was preparing for this session. So what I plan on doing is one of 2 things, or maybe both things. One is I want you guys to be able to get the most out of this as you can. So I'm going to kind of be your mentor here. and tell you you're welcome to give me a call, send me emails about different things that you want to know as you try programming in assembly, and I'll do my best to answer those and get you on your way. Also, in every case that I can, I'll answer those to the group, everybody that attended today, and those that couldn't attend, so that everybody gets the benefit of the questions that were asked and the answers that were given. Also, I think that what we probably will do is have another webinar that kind of takes it from this point and goes beyond into some more advanced material. I'm going to go ahead and take a few more questions and then possibly show another example if there are no more questions. So somebody said, could you offer a real-world example when ASM was needed over spin? Okay, yes, I can. Spin is pretty fast, so in most cases you can use it for a lot of different things. In fact, you could use it to bit bang. You could make a little RS-232-like serial communication routine in spin that can run it up to, I think we figured out 19.2 kbaud if you're running at 80 megahertz. That's pretty fast. It's pretty decent for an interpreted language. But if you want to go faster than that, you really just can't do it with spin. And mainly that's because there's a little bit too much indeterminism in how much every instruction in spin is taking in time. So even with the advent of the wait count command, you can't get by that. You need to go faster. That's a perfect case where you absolutely need an assembly language routine to go faster. So you can get up to 115.2K or faster in the megabauds. In fact, the Propeller, the viewport software communicates at 2 megabaud, and it's only because there's a cog running an assembly serial communication routine. Let's see. Is there a minimum delay for wait count? Very, very good question. Yes, there is. It depends on what language you're using. In spin, I have found that the overhead, the minimum delay is 381 cycles, I believe, and it is documented in the manual, I believe, in the wait count command itself. So you can only wait for a minimum of 381 cycles in spin. In assembly, you can wait for a lot less than that, but most every instruction in assembly takes 4 cycles. So let's take a look at this example that I have on the screen here. I basically take a sample of the current time at this moment. 4 cycles later, I add a value to it. 4 cycles after that, I get to the wait count command. Now, the wait count command takes a little bit of extra time to set up. I believe it's 5 cycles. So I think the minimum delay here is actually 9. This value gets moved. The system counter gets sampled right at the end of this. So there's only 4 cycles afterwards, and then the initial 9 of the wait count command before the cog shuts down. So 4 cycles plus 5 cycles is 9 cycles. I believe that that's the time. I think I tested that once before. So that would be the minimum amount of time in assembly. Somebody asked in the conditions, how is if E used? That's if equal. Let's take a look at that conditioning, and he's talking about this one, if equal. In other words, if the Z flag is set. A lot of times you would use if E if what you had executed was a comparison, like I'll show you up here, like one of these commands, this compare command, CMP. Sorry, your screen has taken a little time to update. The compare command compares 2 values, either signed or unsigned, depending on which form of it that you use. And it stores the results as the Z and C flag. The Z flag gets stored if the destination value is equal to the source. In other words, this is actually doing a subtraction, I believe, within the ALU. And so the Z flag gets set when the subtraction result is 0, which means that both values, the destination and the source, were 0, or excuse me, were the same. So later on, you would want to use if E if you cared whether that operation ended up with comparing two values that were equal. Similarly, you could use if NE, you can see this just below the if E condition, to see if they were not equal. And most of the time, I use just like if C and if Z, because I'm typically not doing just simple comparisons. I'm doing tests for different bit patterns. But if I were doing a comparison, I like to use if E or if A or if B to make decisions about what decision path to take if the values were equal or one was above or below the other. I guess the point I'm trying to get at is you could still use if Z or if Z in that place, but it makes more sense readability-wise in the code that if it's if E, then you're logically thinking, okay, if those two values were equal, then I'm going to perform this instruction. Okay. Somebody asked that this webcast go online. Yes, it absolutely will, and I promise to do it faster than I have on the previous ones. And what we're going to do is take the recording of it and add just a little title screen to the front probably, and then post it up on the web. It'll probably be up there tomorrow. I'll send you guys an email to it. And also later on, we'll take it and break it up into little clips that are topic-based, so people can, review just little sections of it. Somebody asked, is it possible on ASM to set up the counters so they can independently keep track of the time between two pulses? This would presumably not involve a cog except to start or check the counter. Can this be done with maximum accuracy? In other words, by counting the count register. Let me think about that a second. Oh, the question disappeared. I think you were asking, you want to know what the time difference is between two pulses, or the difference between the width of each pulse. Can you do that? I think you can. In fact, I think I've done this before. I believe, though, the only way that I could do it was to, I set up one counter to basically increment as soon as it saw a high pulse, and the other counter to increment as soon as it saw a low. And as long as I came in there early enough in my assembly code, I could catch it and compare the two and come up with my value. Oh, here's the question again. Can I independently keep track of the time between two pulses? I'm assuming those two pulses are on the same line. Oh yeah, if it's two pulses on the same line, I'm not sure if that's the case here. It becomes quite easy. You can just have it watch for a low and increment with every clock cycle, so that gives you your clock count, your cycle count for the width of that pulse. Of course, it would mean that your main assembly routine in your cog would have to be fast enough to, it would have to come back to check that cog or that counter value during the opposite pulse state, the opposite level, in order to see that, okay, it hasn't changed anymore, so this must be the count of the last pulse, and then clear it to 0 and then continue on. So it does require, it can't really be done independently without having the result of one be added to the result of the next pulse. So I guess to answer your question, no. You can't do it independently, but you can with a little bit of effort from the cog, and depending on how fast the pulses are, that might be a minuscule amount of effort from the cog. Okay, and let's see. Oh, somebody asked, if I have a carry flag overflow twice in the code, does the carry flag get cleared? The carry flag will only be modified when you tell it to. So if you had an overflow in 2 instructions, I know this isn't exactly what you asked, but I'm going to answer 2 questions here. If you have 2 conditions that occur that could cause a carry flag set, but only one of them had written the value, the other one that could possibly have caused it that's not writing the value won't affect it. The carry flag will still be set or cleared based on the last operation. If you have 2 instructions that both write the carry and both operations ended up with an overflow, the result would be that the carry flag is still set and you can't tell whether the previous operation had set it or not. So it doesn't toggle the carry flag. It just either sets it based on that one little condition at that point in time or clears it based on that condition in time. As indicated memory consumption by the assembler, how much by the spin? Oh, okay. I could show you that really quick. If we go back to, let's go back to our original example. I believe what you're asking is, I was talking about high and low density code where the spin code generates slightly tighter code, and in some cases an extreme amount tighter than assembly. Here we've got 2 routines, the spin routine and the assembly routine. Both are 3 lines of code, essentially 3 steps. We've got setting the direction state, a loop, and setting the output state, and it's the same in assembly. But if I'm going to press F9 here to compile this, and if you look at the bottom, as long as I have my cursor within the spin toggle pin method, at the bottom it shows me my private method spin toggle pin consumes 11 bytes of space. If I click down here in the data section, I see my data section takes 12 bytes. So, of course, that's a tiny amount. This one, I could have also counted this. This is 1, 2, 3 longs. This thing is 11 bytes. That's just short of 3 longs. It's 2 3/4 longs. I know that there are other examples where the difference is more extreme. Hopefully that answers your question, but it's an easy way to check. Also, I did just click in this data section to see how big it was. This thing on the status bar at the bottom, it shows you how much space that whole data section is taking. So if I have other defined data that isn't necessarily being used by the cog that I launched my assembly code into, or, well, yeah, just in that case, it's going to report a value that's bigger than what your assembly code is. But you always know that every assembly instruction, every executable instruction takes 1 long of space, so you can just simply count them up. Let's see. Could you please provide some details regarding the shadow registers affiliated with various special function registers? Yeah, obviously this is kind of an advanced topic. Let me give you something to look at here. If you take a look at let's see, where would this be? Let's look in the Propeller manual. Wherever sorry, while I find this page. There we go. Okay, so what I'm showing you is table 1.3 in the latest manual, the cog RAM map. The special purpose registers, the last 16 registers have, some of the registers are read-write and some are read-only. Now, in actuality, in the cog, all the hardware is very symmetric. We didn't make a whole lot of exceptions to how something was built. So the actual RAM, the cog RAM, there's a register that is readable and writable in the location where, let's say, for example, the par register is, or the count register, or in A and in B, even though those 4 registers are technically read-only registers. What actually happens is you can write to the what's called the shadow register space, the register that's actually physically there. When you do, I guess what I'm saying is when you use par, count, NA, or NB, it actually is pointing to a physical register that's just like every other register. It's read and write. But the hardware kind of takes over and redirects the result that you get back from a different location, not from that register. So when I read in A, let's say, I get the value that's currently on the input pins, or all the pins that are inputs on the 32 I/O pins, rather than the value that was stored in the this physical location 1F2 in CogREM. Now, there is a possibility of reading those in some cases, and I can't remember exactly how it works. I might have to follow up on this via email. I believe it really comes into play when you use, like, let's say, you can write a value to NA. You're unable to read it, but in certain cases, depending on whether you have it in a source register or a destination register in an instruction, you can actually operate on that value. I'm sorry, I'm kind of drawing a blank here. I know you notice at the bottom there's a note 1 on each of these read-only items, and it says for Propeller assembly, these are only accessible as a source register. See the assembly language section for more information. If you use, say, in B as in the destination field of a particular instruction, what you get is not, I think what you get is actually what's in the shadow register. So you could possibly use that somehow. I think mainly you can only use it to set or clear flags. I'm sorry, I don't know a better answer to that, but I'll look into this and reply to the whole group via email if there's some other little tricks there. By the way, typically you wouldn't want to do this because I mean, if you're doing it, it might be by mistake, and so just be careful with it and pay attention that those read-only registers really need to be in the source field of an instruction in order to be properly used. Let's see, I'm looking through the questions here. Somebody asks, how does one organize a simple spin program that holds separate DAT sections for PASM applications that are intended for separate cogs? Well, you don't need a separate DAT section for separate assembly blocks, but you can certainly do that. Let's take this example here where I have one DAT section and I have one little assembly program in it. I could simply copy and paste that and change some code here. Maybe I want to do a, I don't know, an add here and just an OR here or something. Now I've got 2 separate assembly programs. I do, of course, need unique loops here. I'm just going to, for sake of brevity, change their labels slightly so that it compiles. So now I have 2 DAT sections, and it looks nice on the screen because they're visually separated by the ledger type background color change. And so this is how you could organize it in a spin program to have separate little sections that you might think of as obviously meant for, or separate little assembly programs that are meant for possibly different cogs. You could, however, this is not a requirement, you could simply have them all in the same DAT section, like what I've just done here. And the key point here is that everything else is important, that the labels still, of course, need to be unique, globally unique, and you must have an org statement at the top that is typically org0 or just org, which is assembles to the same thing. And your code at the top, let's say if I wanted to start both of these, I've got my cog new at the top that launches the original instance, and I could simply have one that points to the second, and that gets launched into a second code. I hope that was answering your question. Somebody says, or asks, will the Prop2 chip run Prop1 code? Yes and no. The spin code has not been changed in any way that would cause old spin code to, or most old spin code not to run. Of course, there are some architectural changes that may come into play there that would cause it to behave a little differently that you'll have to pay attention to. We expect that people will tend to write code for one or the other or both, and maybe even separate programs. But the main difference between the Prop2 and the Prop1 as it stands today is all in the assembly. There's a lot of enhancements in the assembly code that will be very beneficial for people. And it won't necessarily not run code written for the Prop1. It just won't necessarily do it as good as it really could. So let's see. If all cogs are running PASM after they are started, can the whole 32K of hub RAM be used as a video buffer, for example? Sure. Yeah, as long as you don't have the need to, launch any other code or change, variables that were being used by that original spin code or that original application. That's absolutely possible. I don't think I've seen anybody do that. It would mean, let's see, yeah, it would definitely mean that every piece of code that's being executed at that point in time must be assembly code. That way you're not relying on any stack space, which is required to be in main RAM, and you're not modifying any variables out there. You're just solely inside of one or more cogs. So yeah, as long as you have, you could have, depending on the complexity of the application, you could have multiple cogs all running assembly routines that you launch from the initial application, and then one or more of them completely overwrite that 32K app in RAM and use it as, for whatever purpose they want. And they can still communicate to each other through that RAM to coordinate things as needed. If I were to use compare destination, source to test a flag for a specific value, I would use if-e to execute code based on that flag. Yeah, that's one possibility. Or if-a or if-b. You could also use if-c, if-z, if not z. Any of those conditions that fit your need and make logical sense for the readability of the code. And the great thing is that you don't have to act on that condition right away. You could, if you don't have any instructions later on that modify the flags, then you can act on that condition that was or that situation that was created hundreds of instructions above, way down below. And multiple times when you act on a condition in a flag, it doesn't change that condition. Those flags are only changed when they're written to by an instruction that you specifically told to write. So you can, for example, I think I have here's a little example that I neglected to show you that was actually using a condition. I'll wait for your screens to update here. What this is I took the assembly toggle pin routine and modified it slightly so that I could have some different behavior. In this case, this is the one that was using weight count, so it's toggling once every, what was it, 100 microseconds, I believe. And what I did here was create a command, or excuse me, a variable that I increment every iteration of the loop. Then I test it here against the binary pattern 1, 1, and I write the Z flag. And the reason I want to do that is because I want to test to see when a multiple of 4 iterations has been reached. Every 4th iteration, I want to do something different. And if you count binary, the first value is 0, 0, which when tested against this will result in 0, which flips the Z flag, sets the Z flag high. And then the next 3 iterations will be 0, 1, 1, 0, or 1, 1 in the variable count, which will set the Z flag to 0 when this instruction is executed. So on the next instruction, where I'm toggling the pin, this XOR out A instruction, I preceded it with a if NZ instruction, which means if not Z. If the Z flag is not set, then execute this instruction. So when the Z flag is cleared, it's going to execute. When it's set, it's not going to execute. And this has the effect of toggling P1 3 out of 4 times, and every 4th time it just doesn't toggle it. So we end up with an extra 100 microsecond delay on the signal. Somebody asked, is there an estimated release time for the Prop2? If there is, I would like to know it. It changes all the time because we're constantly improving it, thinking of ways to enhance it. We are doing parallel efforts. The design is being done in parallel with the layout. So there's quite a lot of it that's already laid out and officially done, but the whole chip isn't done yet. However, we do intend to be doing some test chips that will probably be certain blocks of the new Propeller 2 and not the whole thing integrated together in near the end of Q1 of this coming year. Based on those and how long it takes to lay out the rest, I'm estimating sometime near the end of the year is when we'll actually have a chip available. But honestly, it's really hard to tell. We don't even know. We could find some major problems that we're not really willing to compromise on it very much. So we'd like to make sure it's as perfect as it can be. Let's see. It appears the maximum data transfers between cogs would be about 2 million transfers per second. Does this sound correct, or am I missing something in my estimate? Well, I suppose it depends on how much data is in your data. But if you're just looking at maybe something that's atomic, like a byte, word, or long in size, then every cog, when you're running at 80 megahertz, can access, either do a read or a write on the main RAM once, or like about 5 million times a second. So other cogs can also run at that rate, and if one finishes, the other one can read it. So you could, on something atomic like that, you could get upwards of 2.5 million. So your estimate's pretty accurate. And depending on, you can only access a maximum of 1 long at a time. So I guess, yeah. So as long as your data is not, or what's logically the atomic elements within your data is not so large that it requires more than one read in order to do a processing operation, then yeah, your throughput would be around 2.5 million. Okay. By the way, we just reached 11:30. I'm willing to continue this until noon our time, another 30 minutes. So feel free to stay. If you have to go, by all means do so, and you can catch up on the recording of the webinar later. Somebody said, let's see, assume I can pass values from spin to ASM so I can code in spin for 90%, then drop to ASM for speed. Oh yeah, absolutely. Let me show you an example here. Trying to think of what would be a good example. Well, this quadrature encoder essentially works this way. I'm not going to get into the code, but you can take a look at this code. There's quite a lot of comments in it, so it should be fairly understandable if you read through it. This is essentially a little driver that sits there and it reads up to 16 different quadrature encoders out there that could be spinning at different rates or not spinning at all. And it updates variables that are given to it by a spin routine. So if I take from another object that's written in spin, let's say, and I call this start method, I give it the start pin, the number of encoders, the number of delta values, and a position address. The assembly code is constantly updating those. And what ends up happening is the position address is the address of an array of longs that will be used to store the absolute position of each individual encoder. And the assembly code is actually writing and updating each of those longs within that array as it runs, just freely. The spin code can actually just read that variable. I'm sorry, I don't have an example here that's actually accessing it, but can actually just read any of the elements within the array that it passed, and the value will be updated, or it'll be up to date, I should say. You can also do things like, well, you can have other routines that interface to the assembly code, like, for example, this read delta feature of a quadrature encoder. This is for, most of the time when you're reading encoders, you need to know, has it changed since the last time I read it? A lot of times you don't really care what its absolute position is. Maybe this is something on a free spinning axle, and the absolute value is irrelevant. You just want to know, has it changed, how far, and from that you can calculate how fast. So you do that here with this read delta function that is written in spin in order to essentially interface to the assembly code. And the way it does that is it relies on some variable space that you pass it as some working space where it keeps track of a snapshot of the last time that you called read delta and the current count. And then it does a quick little calculation and returns to you the delta position, so you get a positive or negative value that indicates the direction and how far it's turned since the last time you checked. There's all kinds of little things like this that you can do between spin and assembly. In fact, if you take a look at the graphics driver, that thing relies on features like this all the time, or everywhere, where the graphics driver itself is way down at the bottom, written in assembly, and it's doing actually, the grunt work, the drawing each pixel for whatever element you decide to show on the screen. But there's a lot of spin code that you can see up near the top here that is not just for starting and stopping it, but copying, changing colors, specifying width, drawing lines and stuff. All of these are spin routines that are writing values to a section of memory that was initially passed to the assembly cog when the assembly cog was started. And think of it as it's just a buffer of memory. And the trick we used was the very first value, I believe, the very first memory location indicates the command. Like, are we drawing a line? Are we drawing an arc? Some kind of vector, pixels, whatever. And the rest of the data in that buffer to follow are specific, parameters of that command. And what happens is the spin code, when you call, like, draw line, it gets ready to write values to that buffer. But if it sees that the first command is, the first location in the buffer is not 0, then it knows that we're still waiting for the graphics driver to do something on a previous operation, because the very last thing the graphics driver does is write a 0 to that location so that the spin code can now know that it can freely overwrite the data in that buffer. That way there's no kind of contention between two separately running cogs that are running at different rates. You could also use the semaphores, the lock bits, to achieve the same task. But in practice, we've realized we personally have never used the semaphore bits to achieve something like this, because most of the time we're passing data back and forth, and we can simply just have some kind of flag within that data that each independently running cog can use to determine when it can make the next move. Oh, here's a good question. On that weight count example, is the 80 megahertz divided by 1K calculation that I did declared for the delay, is it evaluated at compile time? And what he's asking about is this down here. And yes, the answer is yes. It's compiled at, or it's evaluated at compile time. So the value that gets evaluated, the value that gets the value that's a result of this expression is what gets stored in this memory location as just data, as a constant value. Of course, that's not super handy, because what if we're not running at 80 megahertz? Maybe we don't know how fast we're going to be running, and we need to make an object that can dynamically change or dynamically respond to changes in the clock speed. So what you could do is read the actual clock speed from main RAM, which is, I think it's the first long. I'd have to honestly have to look this up again, but I believe it's the first long in RAM that you read, and that tells you what the current clock speed is if it was written appropriately by other code that changed the clock speed. And then you can do a division on that to indicate or to calculate, what your delay, your appropriate delay should be, so that you're always delaying a specific amount of time from another device perspective. That actually brings me to a question that was asked ahead of time. Somebody had noted that we have an add command and a subtract command, but we don't have a multiply or a divide. Yes, that's true. We don't have any hardware multiplier or divider, and those are kind of complicated features. However, the Propeller 2 actually will have a hardware multiply and a multi-cycle divide, I believe. I'm not positive about that, but it definitely does have a hardware multiply that's a single cycle multiply. But how do you do it on the Propeller if you need to do multiplication or division? If you think back to, how we were taught way back when we were young, it's kind of an iterative process that, like a multiply of 16 times 2 is the same as 16 plus 16. That's kind of the long way to do it. Of course, you don't want to be multiplying something by some huge number and just have millions of iterations to try to calculate this. So there's got to be a better way, right? Well, yeah, there is. And I actually have some sample code here that I wrote this morning to demonstrate this, actually all I wrote was sort of the wrapper around the code. The routine I'll show you is this little, let me scroll down a little bit further, this little multiply routine that I'll highlight here. This is a routine written by Chip that takes a 16-bit value, multiplies it by another 16-bit value, and returns a 32-bit product. And it works really fast because it's not based on adding a number to itself, whatever the multiplier is. It actually works with the values of the bits. If you think about numbers like in decimal, every digit has a particular placeholder value associated with it, and in mathematical operations, the value of that placeholder multiplied by the value that's in that digit or that decimal place has that type of effect, or that cumulative effect on the operation. We can do the same thing, and you can actually kind of in longhand. I mean, you do this longhand if you multiply by longhand. You just don't realize you're doing it probably. You can do the same thing, but in binary, base 2 instead of base 10. And so that's what this routine is doing. It actually just it goes through 16 iterations, and it's got the product of two 16-bit values multiplied together, regardless of what those, how big or small those values were. So that's really handy. It doesn't take a different amount of time, based on what the values were. So I'll send this routine out to you. This one, actually, I'll show you here. I started up the Propeller serial terminal. This little code that I wrote just interfaces, just serially outputs strings and values to the serial terminal or any terminal of your choice. And what I do here is in the spin code, I have a value x and a value y that I set to 115 respectively. Then I print some things on the screen. Then I call my assembly routine and pass it the address of value x, and I know inherently that I put value y right after it and the result value after that. And the assembly routine simply grabs the address of that, reads the values out, which it does in these lines, and then it calls the multiply routine, which does its thing. Then we simply write the result back and terminate. It's a pretty inefficient use of a cog for assembly, but you get the point here. And if I run this, we'll see what it says on the screen. There we go. Multiplication, 100 times 15 equals 1500. And I did the same thing for divide, which divide is a lot, it's a bit trickier. But we have a little divide routine too. By the way, these little routines, they're in the back of the latest Propeller manual, which is also available for free within the Propeller tool itself. And then I'll show you, it's in Appendix A, I believe. That's where I took those routines from. But I'll send you this source so you can use it as well, just right out of the box. Here we are. It'll take a moment for your screen to update, but in the back of the manual is a section on multiplication, division, and square root, and it has some example code and a little bit of explanation about this. Incidentally, I just noticed this morning that there's a typo in this. It looks like maybe a sentence was erased or mangled somehow, so sorry about that. We'll have to get a little errata out on that. So to get back to what I was originally talking about, which I believe was this wait count instruction, if we don't know what the clock rate's going to be at any given time, we can read it out of the first register in main RAM and perform a division on it or a multiplication to decide how many clock cycles we need to delay to achieve our specifically timed delay. And we can do that calculation, multiplication or division, using one of those routines that I showed you. Somebody said, since most assembly instructions take 4 cycles, a wait count command less than 4 is not possible, correct? Yes, that's not possible. The wait count command takes at least 5 cycles. If you look up in the either the quick reference or in the manual at the wait count command, or all the commands, on the far right side is a column that indicates how many cycles those instructions take. And right here near the bottom, the wait count command takes 5 plus cycles. So it takes at least 5. I mean, typically, practically, you couldn't wait for such a small time because otherwise you wouldn't be doing anything other than waiting, because you wouldn't have time to do anything until, or in between that wait and the next wait that you happen across. So the practical value is probably up in the teens. But the minimum that I've noted was 9 if you're doing taking a sample of a snapshot of what time it is and adding some value to it and then waiting for that. And somebody asked, can you use clock freak instead of 80 million for more general code? That's related to the wait count example that I was talking about. That's a good question too. In fact, I thought so. When I was kind of tired when I was writing this code. Clock freak is a variable that's built into Spin. It doesn't exist in assembly, and it's not something that you can use at compile time. So this expression here, where I'm actually trying to create a constant value that's stored in in the application, I could not use clock freak to create that value because clock freak doesn't technically exist. So that's how you have to resort to essentially reading the contents of clock freak at runtime. And in Spin, you do that just by referencing clock freak. In assembly, you do that by doing a read long on location 0 of main RAM. That's where clock freak actually gets its value from. Let's see. Somebody asked, can you explain the use of jump ret? It's a bit mysterious. Yeah, I can understand that. I'm glad you brought that up because that's a topic I neglected to talk about here. If you're familiar with assembly languages in other processors, whenever they do a call, like to a subroutine, there's a stack involved, stack space involved, and maybe it's like a specific size stack that's maybe limited to 4 calls or something, so you can have only 4 nested calls. When we were designing the Propeller, we didn't like the idea of reserving the limited RAM that we had in the cog for some kind of stack space. We also didn't like the idea of limiting it to a specific number of nested calls. Maybe you have the need for 5 nested calls or 6 or more, and maybe you've got plenty of memory, but there was no way to indicate what the size of the stack should be. We could have made it work that way, but we chose not to because we thought it would be better the way that we did implement it. And that's let me show you the call command here. And for the person that asked that question, how the call instruction works relates directly to how the jump ret works. So we'll get your question answered. What I'm going to do is open up the Propeller manual here and find the call instruction. Something I forgot to mention, I don't know if everybody knows, but earlier this year we released an update to the Propeller manual. It's now at version 1.1. It's of course available for free. It comes with the Propeller tool. The online form is, the electronic form is free, or you could buy an additional printed manual if you want. But all the information is available for free download or within the Propeller tool itself. So there's a lot of information that's been updated in the PDF, and this call instruction is one of them. This section here kind of indicates how it works, and this is what's a little bit strange about the Propeller. In order to get around this whole stack issue, what we decided to do is make the call instruction, it actually stores the next address, the program counter +1 that it needs to return to later. It stores it at the location of the return address of the routine that it's jumping to. So whenever you have a call instruction, like what you see at the top of this little box here, you're calling a routine, which I called routine, and the call instruction requires in the compiler that that routine label also be paired up somewhere with a label called routine_ret, which stands for the return from routine. And that's what the compiler uses to figure this out. So what it does is it actually assembles a jump ret, a jump return instruction in place of this call. And what that instruction does at runtime, the very first thing it does is it calculates the program counter +1 value, stores that value in the source field of the instruction that sits at the return ret command, or the return ret routine, which presumably is a return command. Okay, so and then let me move on. The next thing it does is this is step 2. It jumps to routine, the place where the developer wanted it to go in the first place. Step 3, it executes all the code in that routine. Presumably it gets to the return ret instruction, which is now a return command with the original PC +1 already stored in it. That command is essentially a jump command, and it just jumps to that address that was stored, which happens to be the location right after the initial call. So what this means is you can't have, there is no need for a stack. You could have lots of nested calls so long as the same routine is not being called twice within that nesting. So you could have some pretty complicated code that's calling maybe 5 routines deep. As long as it's not recursive code, it'll work just fine with this method. And the call instruction, I mentioned that that's like a jump. It's actually a jump return instruction. The compiler just accepts call as a simpler, more natural form because that's what we're all used to. Now for jump ret, I'll dive into the details of this. This is actually a pretty cool little command that has kind of a side benefit that we didn't even really realize at the start. The syntax here is jump ret, jump return, and the destination operand is return instruction address. And then the source operand is the destination address that you want to jump to. Like I said, the very first thing that jump ret does at runtime is it takes PC +1 and writes it to the S field of the register indicated by this return instruction address. All right. Typically, that happens to be an instruction that is a return instruction itself, so that thing returns to the original called routine. Then jump ret jumps to the destination address. This is exactly what call does, because call really is a jump ret. But the cool thing about this is that these registers up here for the operands, the destination and source operand, or the return instruction address, the destination address, they don't have to be the actual routines that you, they don't have to be labels of the routines that you want to, effectively call. They could be just variables. And if you look down here, there's this mechanism, well, this feature that kind of came out of this, we call it internally ping-pong multitasking, where you can use JumpRet to effectively make a single piece of code that maybe has two separate tasks. This is assembly code only. Two separate tasks that it kind of interleaves the processing on, sort of like multitasking works on a bigger processor. And the way you do that is you first initialize it. There's some example code here. You create two variables, two long registers that will be used to store the current task address, the place to return to in each task. So I've got a task 1 and a task 2 variable here. Initially, at the start of the routine, I move the address, well, basically, I move the location of second task into my task 2 variable. Then I drop right into the first task, and I do whatever processing I need to do. And at what point I decide that it's a good time to jump to the other task, I call JumpRet task 1, task 2. And what that does, remember that the first thing that happens here is that JumpRet at runtime takes PC plus 1, stores it in the location of this destination register, which is task 1. It's the other variable. So we're storing in the task 1 variable the place that we want to return to, the address that we want to return to. Then we jump to the address that's stored in the task 2 variable. Notice there's no #, no hash in front of this task 2. That's because we're not jumping to the task 2 label. We're jumping to the address that's stored at the task 2 label. So effectively, we've stored our return address in the task 1 variable, and we jump to second task, which is what task 2 was initialized. So then execution all of a sudden ends up down here at second task. It performs a number of routines. Then it says, at some point that's convenient, JumpRet task 2, task 1. The only difference here is that we flip the variables. Instead of task 1, task 2, it's task 2, task 1. This causes the same series of events to occur, which makes execution jump back to where it was before second task was called. Then we continue on, call JumpRet task 1, task 2 again, which jumps back down to where we left off in second task. And you can do this for multiple tasks. You can extend it to 3 or 4 tasks. And there's an example of this in the full duplex serial assembly code, where we do receiving and transmitting in kind of an interleaved set of tasks, where we jump back and forth, partially through each of those routines, and it's quite effective. The only thing that's the downside of it, like I said, we never really anticipated this feature, is there's no context saving. So by that I mean the state of the flags, the C and Z flags. So if you're writing to C and Z and you intend to use that for something in the future, when you jump to another task, maybe that thing's also writing to C and Z and expecting something. That's going to cause the ping-pong multitasking method to fail. Just another note on that is that with that in mind, the Propeller tool 2 will have a feature like this that works a little better, that actually does save the context of those flags, so that you can do essentially true multitasking within the same cog in assembly code. And there's some additional features to throw in there that I won't go into that make it even nicer. For the person that asked that, I hope that answered it. If you please read this section of the manual. It's page 301 of version 1.1 of the Propeller manual. If that doesn't explain it enough, feel free to call me or email me, and I'll be happy to try to show you more how it works. By the way, JumpRet is typically not a very commonly used instruction. People usually use call instead, and then of course the separate jump and return instructions. But the call is really a jump return instruction. Let's see. Can you please show an example of how to pass an array between spin and PASM? Let's see. Yeah, that's actually it's the same as passing just a pointer to any particular variable with one little exception. So, like in this multiply routine, I created an array of longs, and the elements of the array are value x, value y, and value r. And when I called cog new, I simply pass a pointer to the first element of that array, which is value x, the address of value x. Then my assembly routine knows that what it's getting is a pointer to the first element, and it knows that these elements are all long, so it can calculate the offsets to the others. And I'll show you that. Down here we get the first one by just reading the address that was put in the par register into our local address variable. Then we do a read, because that's what we wanted to do there. We read that element. Then we simply do an add of 4. That's because the original element was a long, which is 4 bytes, so we add 4 to it to index the address that we have to the next element. Then we do another read long here. We call this multiply routine in this case. Then we add 4 again to the address that we had, so that now we're pointing to the last element, which is up here, this value r. And then in that routine, we write along back to that. So passing an array is exactly the same as passing just a single variable. It's just that both the spin code needs to have all the elements in that array, logically placed, like we've done in this example, and the assembly code needs to know, what order the elements of the array appear, and what type they are. Maybe there's a mixture of bytes and longs, possibly, but I wouldn't recommend that. I think that might actually get mixed up by the compiler for optimization, so it's best to stick with elements of the same size, either all bytes, all words, or all longs in a particular array that you pass to an assembly routine. Okay, let's see, it is 12:03 our time now. Unfortunately, we're going to have to bring this to an end. I'm going to see here really quick if there's another question that's a fast one to answer. And we have all your questions logged that you typed into the questions window, so I will answer those. It'll just have to be via email or via phone if you choose to call me. Let's see. Oh, as a follow-up to the question about different DAC sections for different assembly routines, won't loading the first DAT section cause the second DAT section to overwrite the first within the first cog? Oh, yeah. Oh, I could see why you would think that. The answer is no, it actually doesn't. Let's see, do I still have that code here? Yeah, here it is. You would think that because there's this org directive here, right? But actually the org doesn't get placed in the application binary at all. It's just something that the compiler uses to properly calculate the offsets of the symbolic addresses that are referenced within the assembly code. So the cog itself is kind of clueless when it comes to figuring out where to place things. It just always does things exactly the same way. You tell it to launch this ASM toggle pin code, and it comes here and it just starts reading here and stuffs this command in register 0, this command in register 1, this command in register 2, and so forth. That continues on down here. The org is a directive. It's not actually in the application image, so the value in the 4th register will be this add that is part of the ASM toggle pin 2 routine. So effectively what happens is by launching the first one, ASM toggle pin, into a cog, you load that into the proper place, but you also load ASM toggle pin 2 right afterwards because they happen to be butted up here in data space. That may seem to be a problem, but it actually isn't because, well, as long as you have any variables or initialized data that are going to be used by, say, ASM toggle pin 1 defined right after the ASM toggle pin routine, then everything's going to be fine because you're pretty much going to ignore or obliterate the upper addresses in CogRAM that happen to get loaded with this ASM toggle pin 2 routine. And of course, when you launch ASM toggle pin 2, it just starts from that address and starts loading 512 longs into RAM, which include stuff we haven't even written. So it might be garbage, it might be a bunch of zeros. It all depends on how the binary image is made. So no, it doesn't cause a problem. All right. Well, I think we're going to have to call an end to the webinar. It's been great seeing your questions. Again, I want you to excel at writing assembly code. It's going to be a trying process if you haven't done it before. Feel free to ask me for more examples. Email me, call me. I'll do whatever I can to get you going. And in the coming days, I will address every question that you've asked before the webinar and the ones that you asked during this webinar via the questions window. So I'll send you an email to that. We might even start a thread on the forum where we answer all those things. But at the moment, I'm just going to focus on getting them answered somehow. Okay, so I thank you very much for attending. This has been great. It's a kind of a complicated topic. I can understand why there's so many people interested in it and why it's hard to really get going and get proficient. So with that, I'll bring close to the webinar. And again, thank you, and hope to see you at the next UPEW show. Talk to you later.